Let me guess. You're staring at the clock. The EST100 Engineering Mechanics exam is literally 24 to 48 hours away, and yeah, the panic is starting to set in. Look, I get it. You're staring down a mountain of modules, some seriously complex dynamics, and a class that historically has a pretty brutal failure rate. But hey, take a deep breath. You are in exactly the right place. You don't need to cram every single textbook chapter right now. What you need is a strategy. You can absolutely still pass this thing, and today we're going to build your bridge to that passing grade.
So welcome to this special edition explainer. Think of this as your focused, high-yield review guide. We've built this directly from the syllabus and, more importantly, from some really strategic data pulled from the 2020 to 2024 past exam papers. We're going to specifically crash Module 1 today. Why? Because mastering the fundamental statics of particles is the ultimate gatekeeper for this course. If you can wrap your head around these core concepts, you completely unlock the ability to solve those terrifying heavyweight numericals later on. Here's our battle plan. First, we'll hit the exam blueprint to snag some easy, guaranteed marks. Second, the Module 1 core laws you absolutely need to know. Third, free body diagram mastery. Fourth, a mock problem walkthrough of a classic, heavy-hitting question. And finally, the equilibrium checklist to make sure you don't drop any silly points. Let's get right into it.
All right, Section 1, the Exam Survival Blueprint. Let's look at the actual historical exam data from 2020 to 2024, because spotting the examiner's patterns is basically half the battle.
So, the data reveals a massive hack for surviving this exam. Part A of your paper is made up of these 3-mark theoretical questions that repeat almost every single year. Seriously, memorizing these specific, recurring definitions is going to guarantee you an easy 15 to 20 marks right out of the gate before you even turn your calculator on. You absolutely need to be able to concisely define D'Alembert's principle, write out the formula for the perpendicular axis theorem, and explain friction parameters like the angle and cone of friction. Honestly, take a mental snapshot of this list right now. Nailing these definitions is your fastest route to building a really solid safety net of marks.
Moving on to Section 2, Module 1, Core Laws. Now that we've secured those quick theoretical marks, let's look at the foundation for the heavy-hitting 14-mark numericals.
Okay, Newton's first law. I know, it sounds super basic, but do not underestimate this. This single law is the absolute backbone for literally every equilibrium problem we're going to solve today. In engineering mechanics, we're mostly dealing with bodies at rest. So what does that mean? It means the sum of all forces acting on our particle or our object has to equal exactly 0. If the thing isn't moving, the forces are perfectly balanced. That right there is the entire premise of your equilibrium equations.
Next up, the Parallelogram Law of Forces. When you're dealing with concurrent coplanar forces, which just means forces acting on the exact same point in the exact same 2D plane, you can't just add them up like regular numbers. You got to account for their angles. This law gives us a really slick geometric trick to combine two forces. Let's call them P and Q. We can use this to figure out their total combined effect, which we call the resultant. And you can see exactly how it works right here. It perfectly illustrates the law in action. Notice force vector P pulling horizontally from the origin point O, and force Q pulling upward at an angle. By just drawing parallel lines to form a parallelogram, that diagonal line cutting right through the middle, labeled R, that is your resultant. Visually, it's just a great way to see how two totally distinct forces combine into one single, powerful directional force. All right, Section 3, Free Body Diagram Mastery. If you want any chance of getting partial or full credit on the numerical questions, you have to master this. You simply cannot skip it. So a free body diagram, or FBD, is exactly what it sounds like. You are freeing the body from its environment. You're mentally stripping away the walls, the floors, the strings, the hinges, the whole shebang. And in their place, you just draw simple arrows that represent the reaction forces those physical things were applying to your object. It essentially deletes all the distracting real-world clutter and leaves you with just the pure, raw mechanics you need to actually do the math.
Look at how cool this translation is in practice. On the left, we've got a physical system, a ball suspended by a string against a smooth, vertical wall. Looks like a standard, intimidating real-world physics problem, right? But then look at the free body diagram on the right. The wall and the string just vanish. They're replaced perfectly by a reaction force, RC, pushing to the right from the wall, and a tension force, FT, pulling up exactly where the string was. Toss in the downward weight, W, and suddenly, boom, you have a simple math problem of concurrent forces radiating straight out from center point B.
Which brings us to Section 4, the mock problem walkthrough.
Let's actually put these theories to work and deconstruct a classic high-weightage exam question.
Okay, when you inevitably flip the page and see a massive 14-mark numerical, whatever you do, don't panic. Just follow these 3 non-negotiable steps. 1. Isolate the body. 2. Draw your forces and reactions carefully to create your FBD. And 3. Apply those equilibrium equations, which usually just means setting the sum of your horizontal forces to 0 and the sum of your vertical forces to 0.
All right, let's tackle 1. Take a look at this classic setup. 3 cylinders, A, B, and C, resting inside a rectangular container. Honestly, it looks like a nightmare, doesn't it? And this exact setup is a super frequent 14-mark question. But remember our strategy. This is not one giant unsolvable mess. It's really just a sequence of 3 very simple free body diagrams stacked on top of each other.
The big secret here is just analyzing the forces at their precise points of contact. So, cylinder A touches the left wall, the floor, and cylinder C. That's 3 reaction points, plus gravity. Cylinder B touches the right wall, the floor, and cylinder C. And top cylinder C? It only touches A and B, plus its own weight. So you just draw 3 separate FBDs. And because of Newton's laws, the force cylinder C exerts on A is the exact same magnitude as the force A exerts on C. To solve the whole thing, just start at the top with cylinder C. Sum your vertical forces to 0 to find the normal reactions, then take those known forces, apply them to cylinders A and B down below, sum your X and Y forces to 0, and you'll find the wall and floor reactions. It's literally just a step-by-step puzzle.
Finally, Section 5, the equilibrium checklist. Before you even think about moving on to the next question in the exam hall, you've got to run through this. Let's quickly run through the graphic excellence checklist. First off, draw a clear, large, free body diagram. Please do not sketch a tiny little doodle in the margins. Make it take up half the page. Second, clearly label the applied loads and the weight acting downwards. Third, draw your arrows for all support reactions. And lastly, clearly write out your equilibrium equations, explicitly setting the sum of forces in the X and Y directions to 0. Look, here is the absolute best tip I can give you. Examiners are specifically hunting for clear diagrams. Often, they're going to award you partial marks just for getting a perfect free body diagram on the paper, even if you completely botch the math later on.
So there you have it. You've got the blueprint for those 3-mark theory questions. You completely understand the backbone of Newton's laws. You know exactly how to strip away the noise to build a flawless free body diagram, and you have the step-by-step method to dismantle a 14-mark cylinder problem. You really don't need a miracle anymore. You just need to apply this exact structure. Focus your remaining study hours squarely on these high-yield concepts. You have the tools. You have the strategy. Now get back to your desk, draw a bunch of free body diagrams, and go absolutely dominate that engineering mechanics exam. But before you log off, I want you to think about this. Which of those scary 14-mark numericals are you going to conquer first with your brand new FBD skills?